Have you ever looked up at the vast, star-dusted canvas of the night sky and wondered what holds it all together? You see the brilliant points of light, the stars, the planets, the faint smudges of distant galaxies. For centuries, we believed that what we could see was, more or less, all there was. We studied the light, we measured the orbits, we thought we had a pretty good handle on the cosmic rulebook. But what if I told you that everything you see, every star, every galaxy, every nebula, accounts for less than 5% of the entire universe? The rest is a profound, humbling mystery, hidden in plain sight. This isn't a philosophical riddle, it's one of the most pressing questions in modern astrophysics. The universe is dominated by substances we cannot see, touch, or detect with conventional instruments. The vast majority doesn't shine, reflect light, or emit radiation we can easily pick up. This invisible component, dark matter, makes up about 27% of the cosmos. It is the silent, unseen majority. Its existence forces us to confront the limits of our perception. Astronomers observed the elegant dance of galaxies and the stars within them. They applied Isaac Newton's laws of gravity. They applied Albert Einstein's laws of gravity. Those laws worked perfectly for falling apples, and for the orbits of planets in our solar system. Yet, when they pointed telescopes to the far reaches of space, the numbers didn't add up. The cosmic ballet was moving too fast. Visible matter didn't have enough gravitational muscle to keep things from flying apart. Something else, massive and unseen, had to be there, pulling the strings. This realization shifted our cosmic perspective. It was like studying oceans by only looking at whitecaps while missing the powerful currents beneath. This invisible mass doesn't just lurk between galaxies. It's right here, in our Milky Way, passing through our planet, and even our bodies, as we speak. Its presence is inferred only through its gravitational influence. A ghostly hand, shaping the structure of the cosmos on the grandest scales. So, what exactly is this mysterious dark matter? Dark matter is a form of matter that does not interact with light or any electromagnetic radiation. Think about why you can see the world around you. This screen your hands the light from a lamp, all because of interactions between light and ordinary matter. Objects reflect, absorb, emit light. Dark matter does none of these things. It's completely transparent. If you could hold a clump of it, it would be invisible, and your hand would pass right through it, feeling nothing. Imagine a dark room with a few lit candles. The candles are the stars and galaxies, the ordinary matter we can see. Now imagine the room is also filled with invisible heavy bowling balls. You can't see them, but you can see their effect. The candles wobble or move strangely, pulled by gravity from unseen masses. That's how astronomers detected dark matter. They watched stars moving in ways visible matter couldn't explain. Dark matter's not dark clouds of dust and gas, nebulae. Nebulae block starlight and emit faint infrared radiation. Nebulae are ordinary matter, protons, neutrons, electrons. Dark matter's different. It's non-baryonic. Not made of the same building blocks. It's a new ingredient in the cosmic inventory. The first major clue in the case of the missing mass came in the 1930s. It came from a sharp-minded Swiss-American astronomer named Fritz Zwicky. He was studying the Coma Cluster, a massive congregation of over 1,000 galaxies. Zwicky measured how fast those galaxies were moving relative to each other. To his astonishment, they were zipping around at incredible speeds, far too fast to be held together by the gravity of the visible galaxies alone. According to his calculations, the cluster should have flown apart long ago. He concluded there must be an enormous amount of unseen mass, dunkle materie, or dark matter. Decades later, in the 1970s, another powerful piece of evidence emerged. Vera Rubin, Kent Ford. They studied the rotation of spiral galaxies, including our neighbor Andromeda. They expected to find that stars on the outer edges would orbit much slower than stars near the bright center. Instead, the stars on the outskirts were moving just as fast as the ones closer in. This flat rotation curve was a smoking gun. It meant the mass of the galaxy wasn't concentrated in the center. It extended far out in a vast, invisible halo. So, if we can't see it, how do we actively search for dark matter? Scientists are tackling this monumental challenge with a three-pronged approach, searching for it in space, trying to detect it on Earth, attempting to create it in the lab. Each method is a testament to human ingenuity, pushing the boundaries of technology to catch a glimpse of this elusive particle. It's a global hunt for a cosmic ghost. Telescopes on mountaintops, detectors deep underground, the most powerful machines ever built by humankind. The first method is indirect detection. We use telescopes to look for the byproducts of dark matter interactions in space. If dark matter particles are their own antiparticles, they might collide and annihilate, producing a shower of more familiar particles, gamma rays, neutrinos. Telescopes like NASA's Fermi Gamma Ray Space Telescope scan the skies, particularly the dense centers of galaxies where dark matter is thought to be most concentrated, searching for an excess of these signals that can't be explained by known astrophysical sources. This is like listening for the faint whisper of a conversation in a crowded room. The second approach is direct detection, which aims to catch a dark matter particle right here on Earth. While we have overwhelming evidence that dark matter exists, we still don't know what it is. This has made it one of the most exciting frontiers in physics, with scientists proposing a host of intriguing candidates. The leading theory for many years has been a hypothetical particle, known as a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are thought to be heavy particles, perhaps 10 to 1,000 times more massive than a proton, that interact only through gravity and the weak nuclear force. This would explain why they are so hard to detect. They would pass through ordinary matter almost completely unnoticed. The WIMP theory is particularly compelling because it elegantly connects the mystery of dark matter with another puzzle in particle physics. Many theories that go beyond our current standard model, such as supersymmetry, naturally predict the existence of a stable, massive particle with exactly the right properties to be the dark matter WIMP. This theoretical synergy made WIMPs the prime suspect for decades, and they have been the main target of the direct detection experiments buried deep underground. However, despite years of searching with increasingly sensitive detectors, no definitive WIMP signal has been found, leading some scientists to consider other possibilities. A second, increasingly popular candidate is a much lighter, more ghost-like particle, called the axion. Axions were originally proposed to solve a specific problem in the theory of the strong nuclear force, but physicists soon realized they also had the right characteristics to be dark matter. Unlike the heavy WIMP, axions would be incredibly light and would exist in enormous numbers, forming a vast, coherent wave flowing through space. Detecting axions requires a completely different experimental strategy, often involving powerful magnetic fields to try and convert the axions into detectable photons. Several innovative experiments around the world are now dedicated to this search. The discovery of dark matter does more than just add a new ingredient to the cosmic recipe. It fundamentally changes our understanding of how the universe is built and how it evolved. Dark matter is not just a passive bystander, it is the primary architect of cosmic structure. Without it, the universe as we know it, filled with magnificent galaxies, sparkling star clusters, our own solar system, simply would not exist. Its gravitational influence was the essential catalyst that allowed the universe to transform from a smooth, nearly uniform soup into the intricate and clumpy cosmos we see today. In the early universe after the Big Bang, ordinary matter was constantly interacting with light, creating an outward pressure that prevented it from easily collapsing under gravity. Dark matter, however, felt no such pressure. Being immune to light, it was free to begin clumping together much earlier, forming vast, invisible halos, forming gravitational wells. As the universe expanded and cooled, ordinary matter was then drawn into these pre-existing dark matter traps. Like water flowing into deep valleys, gas and dust pooled in the centers of these dark matter halos, eventually becoming dense enough to ignite into stars and form the first galaxies. This framework explains why the universe has the structure it does, a vast, sponge-like network of filaments, voids, known as the cosmic web. The simulations based on the dark matter model show that galaxies should form along the dense filaments of this web. Galaxy clusters should form at the intersections, where the filaments meet. When we map the actual positions of galaxies in the sky, we see exactly this pattern. Dark matter provides the invisible scaffolding upon which all the luminous structures of the universe are built. Without it, the initial ripples in the early universe wouldn't have had enough gravitational pull to grow into the galaxies we see today. Furthermore, the amount of dark matter in the universe plays a critical role in determining its ultimate fate. The destiny of the cosmos is a battle between the outward push of dark energy and the inward pull of gravity from all the matter, dark and ordinary. By precisely measuring the amount of dark matter, we can better understand the overall density of the universe And project its future. Will it expand forever, growing colder and darker, or is there a different fate in store? The silent, invisible majority holds the key to answering these profound questions about our cosmic beginning and its ultimate end. Trying to visualize dark matter can be challenging, as it defies our everyday experience. So let's try a simple analogy to bring this abstract concept a little closer to home. Imagine you are building a grand, intricate sculpture out of millions of tiny, glittering lights. These lights represent the stars, gas, and dust, the ordinary matter of the universe. You can see them, touch them, and arrange them. However, to give your sculpture shape and stability, you first construct a strong, transparent framework made of clear, heavy crystal. This framework is completely invisible. Once the crystal framework is in place, you begin attaching your glittering lights to it. The framework's shape dictates the final form of your sculpture. You create long, arching strands and dense, sparkling clusters, all held in place by the unseen structure. If an outside observer were to look at your finished work, they would only see the beautiful patterns of light. They wouldn't see the crystal frame, but if they were clever, they might notice that the lights are suspended in ways that defy gravity. They would realize that some invisible support system must be holding everything together. That invisible crystal frame is our dark matter. This analogy helps illustrate several key points. First, the dark matter frame was there first, providing the gravitational blueprint for where the luminous matter would later gather. Second, the vast majority of the sculpture's mass and structural integrity comes from the invisible crystal, not the lights themselves. In the same way, most of the mass in a galaxy is contained within its dark matter halo. The stars and gas are just the luminous decoration on a much larger and more massive dark matter structure. The galaxy we see is merely the tip of a cosmic iceberg. As you look up at the night sky from now on, I hope you'll see it a little differently. Remember that the brilliant stars and the glowing band of the Milky Way are just the visible part of a much larger, more mysterious reality. The universe is shaped and governed by an invisible substance that we are only just beginning to understand. This quest to identify dark matter is more than just an astronomical puzzle. It's a journey to the very heart of what the universe is made of, pushing the boundaries of our knowledge and our technology. The search is ongoing, with new telescopes, more sensitive detectors, brighter ideas emerging every year. Future observatories like the Vera C. Rubin Observatory will map the sky with unprecedented detail, creating vast new maps of the dark matter distribution through gravitational lensing. Next-generation underground experiments will probe for WIMPs, axions. Every null result, while disappointing, helps us narrow down the possibilities and points us in new directions. This is the careful, patient, and collaborative nature of science at its best. Solving this mystery will undoubtedly unlock a new chapter in physics, potentially revealing a whole new set of particles and forces that have been hidden from us until now. It would be a revolution in our understanding of nature, connecting the largest structures in the cosmos, the galaxies, with the smallest constituents of matter. It's a profound reminder that there is always more to learn, and that the universe is filled with wonders that lie just beyond the edge of our sight. So, I invite you to stay curious. If you enjoyed this exploration into the hidden side of the cosmos, please show your support by liking this video and sharing it with others who might find it fascinating. Let us know in the comments what part of this grand mystery you'd like us to dive into next. With enough interest and engagement, we'll continue this dark matter series and go even deeper into the topic. Thank you for joining us on this journey. Keep looking up.